Okay, so moving on is the next topic is about the method of joins and method of sections. And again, we'll more be tackling on the trusses aspect. Okay, so for trusses, so to solve for the internal forces is mostly what we do in our course in the civil engineering department is that this is the methods in solving the internal forces. So zero force members, the frames and machines, and internal forces are just added topics, and still you're going to be using the concept of method of joins or method of sections to solve for the complete force system of the truss. So most likely is, if I'm going to give you an idea, so method of joins is a long process, and then this one is more likely of a shortcut for method of sections. But it's complicated for a method of sections because you'll be getting a section that will provide you with one unknown force only. So later on that part, so we focus first on the method of joins. So usually, the method of joins is um, it's the long process. It's the so how do you call this in mathematics? So in mathematics, it's the step-by-step process going to the answer. So it's a long process, but your answer is sure because again, since it's procedural and it's step by step, so na siya. So medyo taas-taas ang time for method of joins compared to method of sections. Okay, so our objective for trusses is for you to show how to determine the forces in the members of the truss using method of joins and method of sections. And we need also to analyze forces on the members of frames and machines composed on pin connected members. So probably this one is on Thursday. This one, method of sections, will be on Tuesday. Then of course today is method of joints. Okay, so so most likely when we are dealing with trusses, so it is called analysis of structure because most likely when you see trusses, so murag ang iyang load composition is complex. Okay, so our limitation of our study is that we're going to assume that our connections are pin connected, but in reality it's welded, diba? So kanang mga truss frames sa inyong roof or the truss frames in your warehouse. So those are bolted or um, welded depending on the type of connection the structural engineer will propose. So again, the purpose of analyzing our structure is for us to determine the forces acting in the bars and in the pins or hinges of the structure. So pins or hinges, so we already know this one from the previous topic, so we know how to determine the reaction forces. So we are now more focused on the forces acting in the bars. So acting in the bars, so meaning these are the internal forces. So structures to be studied, so we'll only limit ourselves to pin connected trusses, but there are many types of trusses, and I don't think that it is your line of expertise if you're going to go into deeper with different types of trusses. So objective is to see the internal forces holding the various members of the of the system. So it may be concurrent or non-concurrent forces depending on the problem presented. Okay, so this is what a truss looks like. So it's composed of mainly bars, steel bars, angle bars. It could be C channel, W channel. So I hope you are familiar with these steels. Okay, so for example, if so this one is your truss, and then let's say in the application of the trusses, so this one is your load. So the distribution of the load coming from the top load, let's say it's a bridge. So the distribution of the load will be going to the points of intersection of your trusses. So that's for simplicity lang sa understanding in a simple manner. So meaning the the weight of the bridge will be pointed towards the joint of your trusses. Okay, so that's one way on how to see trusses also. So our aim is to see the different forces interacting in the internal members. So if you can see medyo taas-taas yan, diba? It's a long process because we're going to determine each forces in each member. So these are the different types of trusses. So you have the Pratt truss, the Howe or the Howie truss, the Warren truss, K truss, the Baltimore truss. So Baltimore is used commonly in bridges. So for the other types of trusses, so I think you can see this one in your homes, especially in your roofs. Or for example, if you own a warehouse, so if you look above the ceiling, so you're going to see different types of trusses in your warehouse. Or if you ever go to a warehouse, so probably you can see a different type of truss that has been installed in the structure. So especially the basketball courts in your barangays. So if you look above, so those are the different trusses that holds together the roof of your building or your gym. So sa homes is I don't think you can see the truss because it's already covered with kanang ceiling, di ba? So we also have the Fink, the Pratt, the so Howie. So you can also see this one as your roof trusses. So a truss is a structure composed of slender members joined together at their end points. So this is one good example of a roof truss. So you're going to create a truss first, di ba? And of course, di lang siya duha ka buok, but it's a multiple number of truss. So I think in the inner part as well, so you can create different triangles there or trusses before you put your load or the cover in the roof, or depending what structure you're going to put above the truss. So if you're going to make this complex, so in the aspect of civil engineering or structural engineering, so once the roof is installed, so aside from determining the load coming from the the dead load or the roof load, so of course we analyze it as well using the standards of the wind load and also the standards coming from the code, which is the earthquake load. So daghan pa kay nag-analysis compared to the basic ones, which is just the live load and the dead load. Okay, so notice again that a truss is composed of slender members joined together at their endpoints. So meaning these are the points, yung mga murag pin connected as what we have assumed earlier. And then this one is one member, second member, third, fourth, so on and so forth. So 5, 6, 7, and then 8. So 11 members in total. So if you can imagine, so medyo taas-taas but taas-taas ang process sa pag-determine sa forces. Okay, so this is also an example of the load distribution coming from the bridge truss. So again, since the deck will be placed on this portion, so most likely the load will be these ones. And of course, this one will be the support. That's why it's opposite direction of the load coming from the bridge. Okay, so for connections, so again, most likely the connections presented on site are bolted or welded. And again, we won't be tackling that part, but we'll be approaching our connections in a simple manner. So for actual practice, so this is the actual practice. So it will be bolted, and then it will be placed with a gusset plate, and then a weld pajuja for further fastening of the bolts. Or it could be that there's no bolts, but it's purely welded. So again, it will depend on the structural details. So in our case, is we'll just make it simpler. So everything is connected through a bolt or pin connected. So there's no gusset plate, there's no welding, there's no other types of connection used. So pin connected. Okay, so again, if you haven't seen trusses yet, so you can see it in your roof, you can see it in the warehouses, in your basketball courts, in the barangay. But if you haven't seen other applications of trusses, so these are some of the examples. So the Harbour Bridge in Sydney, Australia. So this one is so I don't know what type of bridge this is, but the components, so as you can see here, so those are trusses. So also the New York City Bridge. So the components also are trusses, as you can see here. So this is the multiple trusses, but as you can see, the design is the same. Okay, so also you have a truss here, but the application of which is different compared to the common use of trusses. Okay, so for our assumptions, so to make our understanding more simple, so all loadings are applied at the joints. So meaning, as you can see in figure B, so the concentrated loads are focused on the joints. So it's not being placed on the member, but it's placed on the joints. So all on the joints of the truss. So members are joined together by smooth pins. So we need to understand that it is smooth because we'll not be dealing with friction at this point yet, or probably you won't be dealing with the friction in the trusses ever jud kay murag trabaho dyan na siya sa structural engineer. Okay, so these members, which are the two force members, will be either be tension or compression. So tension is towards the joint. So let's try to take note here. So tension is away from the joint. And then compression is towards the joint. So as you can see in the figure, so the forces here, this one, so these are all going towards the joint. So meaning these are tension forces. I mean compression forces rather. So this one is away from the joint, moving away from the joint. So this one is the only tension force in the roof truss presented. So the rest are all compressions. So again, since we'll be dealing with the external force and the effect of the external force towards the internal members, so we won't be including the weight of the members in the calculation. So the weight of the members are neglected. So what we will be dealing with are just the external loads, and then the the external loads reaction to the inner loads, or the distribution of the external loads in the different members. All right, so method of analysis is, again, we have two types. So method of joints, method of sections. So first is we'll be going to method of joints. So as you can see here is in the method of joints, so we base on the fact that the entire truss is in equilibrium and also its joints. So meaning the truss is not moving from left to right, it is in static condition. So if it's in equilibrium, so meaning we can analyze the internal forces from different points. So if we're going to be analyzing it joint by joint, so that's why it's called method of joints. So you can start off at A or at C or at B. So that's how you use the method of joints. So of course, before you use the method of joints is you have to solve first for the reactions. And I think is you already know this one coming from the previous topics, equilibrium of particles, equilibrium of parallel forces, equilibrium of non-concurrent forces, and concurrent forces. Okay, so you may start at different points. So in the diagram presented, so it shows the FBD of point B. So as you can see, this is point B. So how did this figure came up? So why was he able to determine that the compression is BC and then the tension is BA, force BA? So of course, if you're going to draw point B first, and then this is the external load 500. So it's safe to say that you need a force going to the left to counter 500, di ba? And again, since your members are just one vertical and one diagonal, so meaning the FBD of the other one to make the joint in equilibrium, so it should be going to the left. Because again, if we try to break this one into its components, this one is the horizontal going to the left, and then this one is going upward. And the upward part coming from the diagonal member will be opposed by the member AB or BA in tension. So that's why it was in this assumption that these forces are in tension and in compression because of the external load coming from 500. So again, we need to remember that we are dealing with equilibrium systems. So it should be that the forces from the horizontal are zero, and then the vertical are also zero. Diba? So muna siya. So 500 will be neglected by this one. The upward portion will be neglected by the downward portion coming from BA. Alright, so this is how it looks like if you're going to draw the truss itself, and then the internal force is just in the inside of the member. So of course you can just draw the FPD and try to avoid drawing the Kwan lang. So this one is for further understanding lang that the forces FBA and FPC are internal forces. That's why i-drawing dire ang truss or ang member. All right. So these are the different types of um, force diagram that you can create from the joints. Okay, so for example, this is your joint here. I mean your truss here at the very bottom part. So if you start with A, if you start with joint A, so this is the first figure, joint A. So notice that if you try to highlight joint A, so you'll only be dealing with three forces, three members. So one is the reaction, the second one is member AB, and the third one is member AF. Okay? So again, the approach here is from joint to joint. Okay, then if you go towards joint F, so notice joint F also has three members. So that will be AF, BF, and then EF. So again, it should be that the forces are in equilibrium. Okay, so if you go to joint B, so 1, 2, 3, 4, 5, so you're going to have 5 forces at joint B. So this is the FPD of joint B. And since you have 5 forces, and again, since it's in equilibrium, so you're going to create a force polygon, enclosed force polygon. So if it's 3 forces, so from joint A and joint F, so you're only having a force triangle. Okay, so if you go to the next joint, joint C, so you only have 3 forces. Then joint E is you have so this one is 4 forces, but it's 3 forces because in joint C, CE member is 0, because if you analyze, the left part and the right part are now equal, and then the vertical load has no vertical load present in that joint, so that will be 0. But it's an advanced topic because it is the 0 force member. So before you analyze the whole system, so you're going to look for the 0 force member first, and then use the method of joints or method of sections afterwards. Okay, so lastly is joint D. So joint D is 3 forces. So you may not understand it right now, but that will be our approach later. We'll be hopping from joint to joint in order to complete the system, in order to complete the analysis of the system. And also, if you're going to look back on this later in the recording, also take note that if we try to um, observe the different forces, so for example in joint A, AF is in compression. So once it transfers to joint P, so it is still in compression, but the direction is again the opposite direction, but it's still in compression because it is going towards the joint. Diba? So for example, you have member AB. So in figure 1, member AB is tension that's moving away from the joint, joint A. So if you go to point B or joint B, so notice that AB is also away, moving away from the joint. So it's still in tension. So dili in tension na but in tension. So just try to pause later this recording and then try to observe the different forces. So notice that the forces are consistent with their direction. So if it's in tension, so even though you are transferring from the other point, so those forces are still in tension. So yan na makita later. Okay, so our procedure for our method of joints is that before again moving from joint to joint is we're going to determine first the support reactions or the reactions. And again, I think you already know how to you already know how to solve for the reactions. So if you don't know how to solve, so try recalling or try going back to the recordings of the equilibrium of particles, equilibrium of parallel systems, equilibrium of concurrent and non-concurrent forces. So those are the topics. So next is we need to draw the FPD for each joint. So again, you start with the joint having at least two unknowns. So if there's a joint having one unknown, so mas maya siya, di ba? So it's better. So draw the FPD of each joint. So you may not also draw all FBD for each joint, but I think you need to draw the FBD if you're going to analyze that particular joint. So joint hopping ta. So when you go to joint A, so draw the FBD. The next, go to point B, so draw the FBD of point B, so on and so forth. So next is we need to assume that all our forces are unknown force member reactions are tension. But I really don't recommend this one because pwede ra siya, but most likely um, it will create confusion because again, if you're going to have tension forces and once you solve this particular member and then the value of which is negative, so ang rule mangunana is you're going to make it in tension. So sige mag-erase sa inyong answers. Okay, so equilibrium equations for the joint system or for the method of joints is just the forces, summation forces of x equals 0 and summation of forces y equals 0. So for the summation of moments equals 0, so that will be used to determine the reaction forces. All right. So again, as a hint to use the joints is that each joint must have only two unknown forces. at least two unknown forces. So if it's less than 2, so it's better. But if it's greater than 2, so you might have a hard time determining the forces. Okay, so let's try to solve our equations. So in the problem is that we're going to determine the force members of DF, this member DF, DF, DG, and then EG. So we're only allowed to use, we're only be determining the forces of three members. So if I were you, so if you're going to analyze it at this point, so where do you want to start? So if you're going to start from A, so notice that super layo ang D and super layo ang point E. So you still have to go through point B and you still have to go to point C. So if you start at H, so notice that um, you're already able to hop into F, which is essential because you can solve DF. And then afterwards is you can hop to G and then solve the rest of the unknown forces. With a simple glance is that you can already tell which joint you're going to start off. So if you start off from A, so you're going to hop into two joints before reaching the essential joints the problem is looking for. If you're going to start at H, so you're already hitting the unknown members that the problem is asking. So we're going to start at H. So 4 panels at 4 meters, meaning these are 4 meters. 4 meters. Okay, so again, the first step is for us to determine the reactions, but since the reactions are already solved, so we can now proceed with the method of joints. So starting with H, so you write at joint H, and then next is you draw the FBD. So this is the joint H, then this one is the vertical load. This is RH, 210 kilonewtons. So one is horizontal member, the other is a diagonal member. So we don't want to assume that it's in tension because again, it might create confusion later once you solve the different values. So instead, we're going to analyze that each joint must be in equilibrium. So since your force RH is going upwards, so there's no other member that is having a vertical load except for the member EF, or FH or HF. So this is force HF. So again, if you try to break down the component parts of force HF, so to neglect 210, so this must be going downwards. And since it's going downwards, it must be going to the right because it should be in compression. So member HF is in compression. So to counteract the horizontal force of force HF going to the right, so member HG is going to the left. So force HG. Okay, so how do we solve for the force system of um, your HF, or the force coming from HF. So most likely is you can create the force triangle. But in my case is di rin ako siya ilibog-libog, but ako lang siyang ikuan tawag na igamitag formula. Kaya naman ni siya shortcut, but di rin ako itudlo ang shortcut kay basin maglibog mo. So let's try to follow what the steps is introducing us. So we use first summation of forces y equals 0. So again, going up, that will be 210 kilonewtons, so positive force for the reaction at H. And then negative force coming from your force HF. So how can we solve for the vertical force? So again, we can use ratio and proportion. So this one is 3, 4. So 3, 4, 5 triangle. So again, if we try to draw the different components of force HF, so this one is force HF. This one is force HF vertical, force HF horizontal. So again, this one is a special triangle. 3, 4, 5, 3, 4, 5. So through ratio and proportion, or if you don't want to use ratio and proportion, you can always look for the angle theta, and then use sine or cosine function. Okay, so through ratio and proportion, so you're going to have, so that will be the diagonal part. So F HF over 5 is equal to the vertical component against the vertical component. So F HF vertical all over 3. So meaning our vertical force HF vertical is equal to 3/5 of the force of HF. So meaning this one is minus 3/5 force of HF is equal to 0. So you're going to have 210 minus 3/5 force HF equals 0. Then you can now solve for the force of HF. So this is 350 kilonewtons. So again, if you don't understand the ratio and proportion technique, so you may use the angle. So solving for the angle, so angle theta is tangent theta is equal to 3 over 4, and then theta is equal to, so this will be 36.87 degrees. So instead of having the ratio and proportion, so since you know that angle theta is 36.87 degrees, so you may use the sine function. Sine theta is equal to force opposite side, so force HFV, then force HF, then you're going to have your force HF vertical is equal to force HF, then sine 36.87 degrees. So instead of this line here, so you're going to have 210 minus FHF sine 36.87 degrees equals 0. So I think you can still be having the same answer for this one. So 350 still. So we now solve one force. So what's left is to solve for the other force. So summation forces horizontal now at this aspect. So force of the horizontal component coming from HF. So again, by ratio and proportion, that will be F HF all over 5. So you always refer to the hypotenuse. And then F HF horizontal all over 4. So this will give you force HF horizontal is equal to 4/5 of the force HF. All right. So again, in formula, this one is going to the right, so that is positive 4/5 for HF. And then minus, because the force of HG is going to the left, that's in tension, minus force HG equals 0. So this will be 4/5 times 350. So solved from the last equation. Then minus FHG equals 0. So your so force Hg is equal to 200 kilonewtons. That's in tension. So tension, and these one are in compression. So again, if you're going to solve this one using the angle, so you're going to have cosine theta is equal to FHF horizontal, then FHF. So FHFH is equal to FHF cosine theta. So this becomes FHF cosine theta, then minus force Hg is equal to 0. So you have 350 times cosine 36.87 degrees minus force Hg is equal to 0. So force Hg is still the same. That will be 280 kilonewtons in tension. So if we try to draw the diagram, the direction, so force HF is in compression. So this is in compression. So meaning if you move towards joint F, it's still in compression, moving towards the joint. Now, member HG is in tension, so that's away from the joint. And then, of course, if you move towards joint G, so member HG is still moving away from the joint. So I think you can see the difference, diba? So that's how you solve the joints. So taas kayo siya, no? So that's what you'll be dealing with in your assignment siguro. Okay, so next is again, since we already solved this one, so this one is in compression. This one is 350 kilonewtons. Then this one is in tension, 280 kilonewtons. So if we try to observe the next joints, F and then G. So if you're going to hop onto the G joint, so our unknown forces or unknown members are three, diba? Member FG, member DG, and member EG. So again, as what has stated ang state earlier sa tips is that we're only allowed to deal with two unknown forces. So if you're going to hop into point G, so you're going to have three unknown forces, but if you hop onto joint F, so you'll only be dealing with two unknown forces, which is member DF and member FG. So we go to joint F. So at joint F, if we try to draw the FBD, so this is the vertical load, the external load. This is 120 kilonewtons. And then one member is unknown. One member is horizontal. Then this one is compression. So this one is compression. This is coming from the previous joint, which is 350 kilonewtons. So we can try to break this one down. So if this one is going to the left, diagonally going towards the left, so it's common sense that our member DF, to make the horizontal component in equilibrium, so this one should be going to the right. Force DF, right? So again, as coming from, and then our vertical load, so we don't know yet the value of the vertical load for member FH. So I mean FG. So ato na siyang i-determine later. So ang pinakasimpulan is we're going to start off with by determining the system components of the 350 diagonal force. So ganina is the angle is 36 point, ilan ito? 36.87. So getting the horizontal component, that will be 300. So HF horizontal. So that will be 350. So ato lang step by step pa para makita ninyo. So to start off with the horizontal load, that will be cosine 36.87. And then we're going to have the adjacent side, which is the horizontal component, force HFH all over force HF, which is 350 degrees. 350 kilonewtons. So this is FHFH, and then this is 350. Okay, so this one is the horizontal component, HFH is equal to 280 kilonewtons. So this one is 280 kilonewtons. So for the vertical aspect, you're going to have sine 3687 is equal to the horizontal HF component over 350 kilonewtons. So force HF vertical is equal to, so it's equal to 210. So 210 going upward, 280 going to the left. So notice 210 going upward, and then you try to minus it with 120. So napay sobrang 100, mga 90, di ba? Mga 90, almost 90. So to counteract the 210 kilonewton vertical force, so it should be that force Fg is going downwards. So force Fg. So again, we know that the force Fg is going downwards because we analyzed it. We analyzed the system components of the diagonal load through these solutions. Yeah. So we know that the upward force of the 350 diagonal force is 210. Then if you try to subtract it by 120, so notice na wala siya kuwang pa, di ba? To make the system in equilibrium. So ato pa siyang punan og force Fg of a certain amount to make the joint in equilibrium. Right? So summation forces horizontal first is equal to 0. So at joint F, so FDF is going to the right, and then minus the horizontal component of your force HF, so that will be minus 280 equals 0. So again, that will be 280 because it's coming from here. So sige, ato lang isuwat kay para sure jud siya ang ma-review ninyo. So minus the horizontal component of member HF is equal to 0. So again, as what have been solved earlier, so this one is FDF minus 280 kilonewtons is equal to 0. So meaning FDF is equal to 280 kilonewtons. And that's in compression. So compression and then compression. So ato na na-solve ang member TF with this joint. Okay? So sakto ba? Member paano to, no? Okay, so next is we solve for the vertical component, summation forces Y or vertical na F bilang na ganina kay Y itong gamit is equal to 0. So this will be force. So we try to consider first the positive parts. So the force coming from the vertical component of HF, and then minus the downward force coming from FG, and then minus the external load, the 120 kilonewtons, equals 0. So again, the vertical component coming from HF has already been solved prior to understanding the direction of your other forces, other member forces. So this is 210, then minus FG, force of FG, member FG, and then minus 120 equals 0. So force Fg is equal to 90 kilonewtons, and that will be in tension. So this is in tension. This is in tension also. So this is 280 kilonewtons. This will be 210, 90 90. All right, so we have solved df, and what is remaining now is the unknown forces the problem is asking, which is dg and eg. Okay, so let's try to copy it again. Kuha ni siya, compression. It's ni siya, medyo taas-taas yun siya nga. So compression, this will be 350. Compression, this will be 280. Tension, this is 90. Then this one is in tension. Sakto ba tension? 280. So now if you try to look at member DG, so the only unknown members are two, which is member DG and member EG. So we can now solve this joint and complete the problem. So at joint G, so this is the joint G, and then this one is the diagonal member DG. This one is the horizontal component EG. This is the vertical component 90, so in tension, so moving away from the joint, 90 kilonewtons. Then moving away also is your 280 kilonewton force coming from HG. Okay, so let's determine first. So since we're going to be dealing with three horizontal components, because this is the one coming from EG, you have the 280 force, then you also have this force here coming from DG. So again, if we try to break it down even further, so this will be the system components. So we have 90 going up, so obviously this should be going down. Then since it's going down, so meaning this one is towards the joint. The behavior of your force DG is in compression. So it's in compression because the vertical component of the member DG tends to counteract the 90 na tension load. Okay, so also notice that these are the same triangles. So it is proportional 3, 4, 5 gapon, or the angle. So the angle for this one is the same as this one here. So it's still 36.87. So in shortcut, so if you are already quick with your trigo, so upon drawing the force triangle, So this one is FDG. So let's say this one is DG vertical, then DG horizontal, and this one is angle theta. So DG vertical is equal to FDG, then sine 36.87. So that's just my way lang ha kay kanang kibawa naman kung sa resulting ani, but if you want to make it step by step, or if you want to make your answer sure, so you can try to write each step lang jud to make your answers kanang sure jud. And then f dg, so cosine 36.87. So looking at your horizontal component, dg is going to the right, 280 is going to the right, so it's safe to assume that your force EG is in tension going to the left to make the system in equilibrium. Okay, so summation forces horizontal is equal to 0. So going to the right is FDG horizontal or DG horizontal, and then plus 280 kilonewtons, and then minus one force going to the left, which is force EG, is equal to 0. So looking at your horizontal component, so you have two unknown forces because you don't know yet the value of dg, I mean FDG. So to do that is, since we cannot yet solve the horizontal component, so let's try solving the vertical component first. If we can solve for dg, so 1 is going up, that will be 90, and then plus dg minus the, minus, because it's going downward, is equal to 0. So you have 90, and then minus so f dg, oops, sorry, f dg, and then this will be sine 36.87 equals 0. So you can now solve for force dg, which is equal to, so which is equal to 150 kilonewtons. So this is in compression. So meaning your member dg is in compression. So this is 150 kilonewtons. So lastly is again going back to your dh. So this one, your horizontal component. So this one is f dg cosine 36.87 plus 280 minus f eg equals 0. So FEG is equal to, so that will be, this will be 400 kilonewtons. And again, since it's moving away the joint, it is in tension. So this is in tension 400. So we already solved the three components the problem is asking for. Okay. So do you have questions or clarifications? So it may be a bit to swallow, but muna siya ang concept for method of joints. Okay, so don't have questions, so let's try to proceed with the second example. So let's try a shorter version lang. Or I think ako lang ni siguro siyang i-assignment. Sige, I'll make this as an assignment lang for you to understand the concept.